Hi, what I have on the workbench today is a Tweezers style LCR meter from ZOTEK. The model number is ZOYI ZT-MD1. LCR tweezers are a must-have if you do a lot of SMD work, as those components are so tiny. It would be very unwieldy to measure with the standard multimeter probes. Now, of course, sometimes you can buy tweezers probes and use those with your standard multimeter, but still having a dedicated meter like this one will definitely come in handy. For just over $30, the ZT-MD1 is certainly quite affordable. And by the way, the full product name is LCR Tweezers Bridge Tester. And what they mean by bridge tester is because the tweezers can measure dissipation factor, Q factor, which traditionally were measured by bridge circuits. Nowadays, all proper LCR meters can do that. Anyway, in this video, we will put it through its paces, and you can see for yourself if it is something you would like to add to your lab equipment collection. Now, here are some of the basic specifications. The resistance measurement range for this meter is between 10 milliohms to 10 megohms. It can measure capacitance between 1 picofarad all the way up to 30 millifarads. And also it has an inductance measurement range between 1 microhenry and 1 henry. Actually, here is the included product manual. Now, the print is quite tiny, as you can see. You can't really read without squinting, but here are the specifications. If you look at the spec, you can see that the meter is actually quite accurate. Depends on the mode and ranges and the measurement frequency, the error is actually between 0.5 and 5%. For resistance measurement between 1 ohm and 1 megohm, the accuracy is between 0.5% and 1%, which is not bad at all for a device like this. As I mentioned earlier, it can also measure ESR, the dissipation factor of capacitors, and quality factor of inductors. Of course, it can also measure diodes. One thing it doesn't offer is voltage measurement, but that is understandable since it is advertised as an LCR meter only. It would be good though if the maximum tolerable input voltage is specified somewhere, but I couldn't find it on the manual. Another thing that's missing from the manual is the resolution of the meter. I guess we'll need to find out. The meter comes in this nice carrying case. As you can see here, it's nice and compact. You can definitely carry it around in this pouch. And here's the meter, and also we have a USB cable that is for charging and also to update your firmware. Alright, let me remove the protective film on the screen here and we can power it on and do some tests. Alright, let's take a look here. So you can see here is the power button, the far right one. Let's press and turn it on. And it powered on relatively quickly. Upon powering on, it enters this auto mode, and it will try to detect the type of components you are trying to measure here. You can see that I shorted the leads, and it's measuring resistance now. But it has some limitations, which are clearly specified in the manual, especially, for example, if the components is in some borderline, then the meter might be confused. But anyway, so that's the measurement. My personal preference though is to manually select the measurement category by pressing this button here. You can see it then cycles through resistance, capacitance, inductance, and diode, and continuity here. So that is pretty easy. Of course, it goes back to auto here. But first, let's take a look at the manual options here. To get to the menu, I think you press, maybe it's long press, the middle button here. Yep, now you can see we get to the menu option. Let me tilt the screen a little bit. I think this way it comes up a little better. And you can see we can set up language. The direction here is essentially set up the display, whether or not you are left-handed or right-handed. If you are left-handed, then the screen would be turned upside down. Should we try that? Let's do that. Of course, if I do this, yeah, it will be upside down. Now we have to do it again here. So let's do menu. And let's change it right side up here. There we go. So that's that. And let's see what else we got. Then you can change the volume of the sound. And let's leave it as 100%. Backlight. Let's see if we can make it dimmer. Does it show up better on the camera? Yeah, I think dimmer shows up better on the camera. Okay, so let's do 50% here. And to be honest, it's actually already quite bright. But anyway, so then we'll have timer. How long does it take for the device to automatically power off? Let me change that to, let's see what we have here. 20. Does it have infinite? Nope, so the maximum is 120 minutes. Then you can do calibration based on the set of resistance values which are defined in the manual. And you can restore factory default and about. So we're at version number 1.4 here. And again, by default, it is measuring automatically. But I mentioned earlier, I prefer setting it to a specific mode. And the reason is, for example, if I'm holding this lead here, you will see it's trying to measure capacitance, whereas this is really resistive load. That is the reason I typically set it to a specific mode. For instance, in this case would be resistance. Now, the update rate seems to be on the slow side. It is roughly 1 time per second. But for LCR meters, this update rate is actually quite typical. Even on some more expensive meters, the update rate would be in the same range as well. So that's really not a problem. You probably have noticed we have two numbers up here. The numbers are currently 0.6 and 100. And that's the measurement voltage and frequency. You can change these two independently. To change the measurement frequency, you can see here, this one says frequency and manual because long press is for manual, so short press is to change the frequency, and we can cycle through 1K, 10K, and 100. To change the measurement voltage though, you will need to long press and hold the hold and level button. Because if you just press it, short press, that's actually hold. And that makes sense because you want to be able to press it quickly to hold the value instead of having to long press it. But to change the measurement voltage, you just need to long press it. So for example, we have the option of 0.3 volts and 0.6 volts. I have to say though, the long press and short press behaviors of these two buttons are a little bit inconsistent here. It depends on the mode you are in. You can see we have secondary displays at the bottom here. For instance, right now we're in the resistance measurement mode. You can see we have the series resistance and the Q factor. The series resistance and resistance measurement should match if you are measuring pure resistive components. In capacitance mode, you have the series resistance, which is the ESR, and you also have the dissipation factor. The dissipation factor is essentially the reciprocal of the Q factor. In inductance mode, you can see we also have the series resistance and we have the Q factor here as well. Alright, the first thing I wanted to do is try to figure out the counts of this meter as it's not specified. So let's take a look here. And here we have a 1K resistor. So let's take a look. We're measuring 976.6 ohm. And of course, the actual value doesn't really matter because we want to see the counts. And here is a resistor of roughly 330 ohms. Let's take a look here. So remember, right now the loss resolution is 0.1 ohm. We have 322.4 ohms here. So now let me put these two in series. And let's take a look at the measurement here. And you can see we're measuring 1.3 kilo ohm, but we lost the last significant digit. So this clearly is a 10,000 counts meter based on our measurement. Now let's take a look at the resistance measurement accuracy here. For that, I'm using this 100 ohm 0.1% tolerance precision resistor. And if you take a look at the manual, you will see that the measurement accuracy is actually dependent on the range and also, of course, the frequency. So for 1 ohm to 1K, you can see here, if we're using 100 Hz to measure, we'll get an accuracy of 1%. But if we are using 1 kHz and 10 kHz, we would get an accuracy of roughly 0.5%. So let's start with 1 kHz here. And that's the current frequency here, you can see. And we get pretty much spot on 100 ohm, 100.1 ohm. And that is well within the tolerance. And let's change to 10K. Yep, we're getting exactly 100 ohm. And let's change it to 100 Hz. We're measuring 100 ohm. So you can see here the accuracy of this meter, at least for this measurement, is very accurate. Next, let's measure a 100 nanofarads capacitor. For that, I first will change it to capacitance measurement mode. And let's give it a go. I want you to pay attention to the series resistance and dissipation factor. can see we're measuring roughly 84 nanofarads with a series resistance of 38 ohms and a dissipation factor of 0.0019. Now let's measure a larger capacitor. This one I have here is, you can see, a 15,000 microfarads capacitor, and let's give it a go. Let me actually first change the frequency to 1 kilohertz, as it's a larger capacitor here. And you can see we're reading roughly 16 millifarads with a series resistance of roughly 16 milliohms. So let's remember those numbers and we'll compare with a handheld LCR meter. And here we have the ET431, and you can see we have already set the measurement frequency to 1 kilohertz with a measurement voltage level of 0.6 volts. So we're good to go. So let's put it on. And we do have some variation, but both of these are in the same ballpark. Now let's try an inductor. Here I have one marked as 221, which is a 220 microhenry inductor here. So let's give it a go. And I'll change it to measure inductor. Let's do 1 kilohertz. Let me put it down. And you can see we're measuring a 218 microhenry with a Q factor of 4.6, 4.7. So let's remember those numbers and we will use a handheld LCR meter to verify. And you can see for the inductance measurement, actually we're very close here. The Q factor is 4.7 and the measured inductance here is 219 microhenry. So the results from these two meters are actually very, very close. Next, let's take a look at the diode measurement mode. And I'm a little bit worried here because the voltage here is at 0.6 volts. As you guys know, most of the PN junction for a silicon diode is at 0.7 volts. So I wonder if we are able to measure that. But first, let's start with a Schottky diode. And let's give it a go. Yeah, for a Schottky diode, you can see we are able to measure the forward drop voltage. This is 0.5 volts. And interestingly, you can see here, we do have a symbol indicating that here is the anode and here is the cathode. So let's actually swap it to see if we are able to measure it the other way around. Yep, as you can see, we can measure this way around as well. So, which means this is using an AC signal to do the measurement. We will take a look at the waveform in a little bit, but definitely you can measure a Schottky diode with this meter here. So now let's measure a standard PN junction here. Actually, before we do that, let me reduce the level here and see if we are able to measure that. No, as expected, you can see here 0.3 volts is not going to work because the voltage drop here is 0.5 volt. So let's change it back to 0.6 volts and let's just verify a PN junction from a transistor here. Yep, as expected, we're not able to measure that, which is a pity. If it has one more level, for example at 0.9 volts, then we would be able to measure a standard silicon diode with no problem, but we don't have that. So something to keep in mind. And as expected, you can see here on the oscilloscope, the waveform is essentially a sinusoidal at 1 kilohertz. So that is a waveform it is using to measure the components. And right now, it has a peak-to-peak voltage of 1.7 volts. And now let's change it to 0.3 volts. And you can see the amplitude dropped. So the peak-to-peak right now is roughly at 880 millivolts instead of the 1.7 millivolts. And of course, if we change the frequency here, you'll see that the frequency changes accordingly here. That's to be expected because that's the measurement frequency. And if we change the mode, I don't think the waveform can change. Yep, essentially every single range is using the same AC signal for measurement as we expected. And of course, it also has this continuity mode. So let's give it a go. You can hear that the measurement is pretty fast. Now, I don't know if this is latched or not. Let's take a look here. No, I don't think it's latched, but because these are gold-tipped probes, the response is actually pretty crisp. Of course, so far everything we have measured can be also done with a handheld LCR meter, but having the form factor here actually makes it very convenient to measure SMD components on the circuit board here. So let me demonstrate. For example, let's say we wanted to measure this capacitor here, and we can just grab it, and you can see we are measuring 31.6 nanofarads. And let's do another one. Let's do a smaller one. You can see that we have no problem either. These are the bypass capacitors. They all have the same value. And let's do a resistor here. Let's find a resistor, this tiny one. And you can see we are able to pick up the value in circuit. And this is where actually the voltage comes in. And while measuring in circuit, you probably want to use the voltage as low as possible. So in this case, let's do 0.3 volts, because there may be a diode junction somewhere, and if you're not careful, you would essentially make that conductive, and that will affect your measurement. So let's do the measurement again. Let's measure this resistor here. And we're having a reading of 630 ohms. So you get the idea here. Using tweezers, you can easily pick up these values, which is going to be very difficult to do if you are using a standard handheld LCR meter. So let's take a look at the inductance as well. And we have a few of these 221 inductors. Let's pick one of them. And you can see we're measuring 256. Now, in-circuit does affect its value, but these are relatively in the ballpark. And do another one. You can see that we're picking up with no problem. All right. Now, I do want to open it up if I can. There is a single screw here at the back. I'm not exactly sure whether that's a screw for the case or perhaps for the tweezer's arms. Anyway, the only way to find out is, let me remove that. Let's see if we can open this, or no, it's not for the, actually, wow, I'm actually surprised I can just open it up right away. Let me zoom in and take a closer look. So you can see on top here we have the battery, and of course the battery has the protection circuitry. And it is, let's see here, it's a 400 milliamp hour battery. And it's soldered on directly, so I need to be careful. But that makes sense, as an actual connector would be too big, and it won't be able to fit into this small space. Now, interestingly, you can see that the arms are actually made of these PCB materials. These are just PCB board, not sure if you can see, instead of some metal pieces. That's actually quite clever. That will definitely cut down the material cost. And of course, you can see the probes are actually sandwiched between these two slots, so you wouldn't add additional stress on the PCB itself, especially the joint. Now, I bet the microcontroller is right underneath this insulation foam. So let me try to peel it to see if we can get anything. I don't want to use a metal tweezer here because it will most likely cause some problem here. And I can't really see from this angle. Let me try to get my macro lens out and take a closer-up picture. Alright, hopefully you can see this. The microcontroller used here is a 32F, which is by Artery. This is a ARM Cortex 32-bit controller here. And we also have a few of these 8-pin, 10-pins devices, one of which is an op-amp. The other two, I don't recognize the abbreviation here, so you'll have to look them up. But overall, you can see the construction here is very neat and very compact. By the look of it though, it doesn't seem that we have much protection on the input side. So that definitely is a concern. You just need to be very careful to make sure that you don't input a voltage, because this is a LCR meter and not supposed to be measuring voltages. And by inputting a voltage can definitely damage this device. It would be ideal if they can specify the maximum input voltage tolerable by this device. Okay, that's pretty much what I wanted to cover in this video. The ZT-MD1 is actually quite useful, and it is pretty accurate. Of course, it would be even better if it could measure voltages, but that clearly was not the destination of this product. Overall, it's a great little LCR meter, especially considering the price. Anyway, I hope you liked the video. If you enjoyed it, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. I say this every time, but really, your participation makes videos like this possible. Thanks for watching, and I will see you next time.